So what if we have real data? So my data is real, which is like temperature, velocity field. Okay, so we want to do Fourier transform of such data. Then this data point satisfies certain property. An important property is this: f hat of minus n equal to f hat of n complex conjugate. So this is complex conjugate, and it's again very easy to see. F hat of minus n equal to, so 1 by n fj e to power. Now this part will become exponential I 2 pi j n by n, right? Because n has been replaced by minus n. Now what is the relationship between these two? They're complex conjugate of each other, right? So I can write whole, well, and what about this? Fj complex conjugate is same as Fj. So I rewrite the inside, I rewrite them as like this: Fj exponential. I put a minus sign inside. Give me 1 minute, I'll tell you. And put a complex conjugate on top. Okay. So complex conjugate of this is that. Complex conjugate of Fj is itself. So no problem. And inside the bracket, what is this quantity inside the bracket? It is f at n. So f at n star. Okay. So that's what we got. So f at minus n, this one, equal to f at n star. Okay. So this is an important property. It must satisfy your Fourier transform. If you compute from using a, I mean, you compute it, and you must get this. So as a result, this is my Fourier space. So physics notation will be -3 for 8 data points to 4, but minus f at of -3 is same as f at of 3 complex conjugate. So we do not save these negative values. Okay, so Fourier transform for negative wave numbers are not saved. So in computers we save only this part, 0 to n by 2. Now there are 5 wave numbers, no, 0, 1 to 5, 0 to 4. So you may think that there will be 10 real numbers, right? Because each complex number has a real part and imaginary part. So it turns out this is real and this is also purely real. For real f0 is nothing but average. F hat 0, right? F hat 0 will be, all the exponential becomes 1. So if this is mean fat is average, and this one is plus minus sum with plus minus. Okay, so these two are purely real. So, and this part is of course complex. So overall we have 8 real numbers and 8 coefficients in the Fourier space. 8 coefficients are only 5 of them, but if you look at the real part and the imaginary part, there are only 8 real numbers. Okay, so it's consistent. We can't have more in real space and less in Fourier space, or more. That won't be one-to-one transformation. Now let's look at 2D. What happens in 2D? So in 2 dimensions, or in fact this for higher any dimension, this for any dimension. So we can easily generalize it. So we have, let's say in 2 dimension we have x and y. So you make a grid of the real space. Okay. Now, so instead of j, I'll have jx and jy. Right? So indices along jx and jy. So here, you remember in physics we have e to power I k dot x vectors. So it becomes I equal to e to power I kxx plus I kyy. So this is a sum, right? For 2 dimension it is 2 of them. In 3 dimension 3. In 4 dimension it is 4. So this is basically sum over dimensions. So JL and L. So this L is the dimensionality. Okay, and I'm using Einstein notation, so this is a sum. JL and L is summing over all space dimensions. Okay, So I didn't put a sum here, but it's implicit. Okay, and so my real space indices are Jx, Jy, J, Z, and so on in real space. In Fourier space also there are these indices. Okay, so we have Nx, Ny, Nz, and so on. Okay, so this is that in condensed matter physics it's called what? Okay, I forget. It's a basically in Fourier space these are indices. Okay, so let's look at the diagrammatic representation. So we have real space. So real space indices go from 0 to nx minus 1 and y direction 0 to ny minus 1. Okay. In Fourier space, of course, this will be nx and y. So this is also going to be going from nx minus 1 along x and ny minus 1 along y. Okay. So this is discrete Fourier transform. So I'm not really doing any continuous Fourier transform. Great. So number of points must be same here and here. When you have real data, then again the reality condition for 2 dimension is this. So f hat of minus n vector equal to f hat of n vector star. Okay, so minus n will be minus kx minus ky. Okay, or minus nx minus ny, and here it is kx ky complex conjugate. Okay, so as a result, in 2 dimensions we do not save half of the data. So I'm not saving this part of it. So this is my, well, along x direction is going up to nx minus 1. For y direction, I keep only the positive kx, 0 and positive kx. So it is ny by 2 plus 1. Okay, and all the negative kx are not saved because of this. I would also want to make a comment that is, if there is some relation, there is a relation between the numbers that must be satisfied, then you do not save them in computer, both of them, because it will be your headache to ascertain this relation. Okay, so don't save it if there is certain relation. That is why for periodic boundary condition we do not save the data points at both ends, because then every time you have to ascertain that okay, this L is same as a value at L is same as value at 0. Okay, so we do not save this part. There's one catch. What about when ky is 0? When ky is 0, then I get f hat of minus kx 0 equal to f hat of kx 0 star. Okay, so ky is 0 on this line. Now, here I have all the values. But please remember, from 0, 1, 2, 3, 4, 5, 6, 7. So till here it is positive, no? Positive kx. From this point onward is a negative kx. Okay. So for this part, I'd ascertain that this will, remember, this will correspond to minus 1. Okay, this is minus 1. So this must be same as f1 complex conjugate. Okay, so we have to make sure that f hat of the kx equal to minus 1, the Fourier component amplitude is complex conjugate of that corresponding to kx equal to 1. Okay, so this has to be ascertained when you are doing especially simulation. We need to put that in real. Okay, so this in fact this is called reality condition. So this is the condition imposed on f hat because f is real. So this is when you do big simulations of hydrodynamics or any real field, electromagnetic field, which really E is real. No, so we need to ascertain this. Okay, so derivative using Fourier transform. Okay, so let's do it quickly. I have 8 minutes left. So we have a function fx and I write this as a Fourier series. Now I want to compute the derivatives f of x at discrete points. Well, let's first write down mathematics. So df by dx is, so the derivative d by dx will not do anything to f at n. It's a not function of x. So this is f at n. But d by dx will act on the exponential, and it will pull out ikn. Okay. Now this gives us an idea. So if I want to compute df by dx, what should I do? I take the Fourier coefficients f at n and multiply that by corresponding wave number f at n kn and put in I. Okay, square root of minus 1. Now once we get these coefficients, right, so there are n of these, capital N of these, number of data points. And then we can do inverse transform, right? So given this Fourier coefficients, I can do inverse transform, and the inverse transform will be df by dx. So IFT, inverse Fourier transform. Okay. So is there any error in this analysis, in this computation? This computation has zero error, right? Because this is following from mathematics. There's no computation involved. There's no round off, nothing. No Taylor series. Unlike finite difference scheme where there is a truncation, right? For n point, well, 2 point, 3 point, 4 point, there are always a truncation in the series. This is exact. Only catch is that I need to have all f at n. That means given a time series or given a signal, I should get hold of all the Fourier coefficients. Okay. Now that is could be expensive, but it is always doable, right? So let's say we have a speech signal. Speech signal for very high frequency or very low frequency, there will be no amplitude, right? I cannot generate very high frequency beyond audible, and I cannot generate very low frequency. Okay, so there's always a cutoff for any signal. So you need to know the cutoff, and once you have the cutoff, then you can pick all f at n's, and this is exact. Okay? So that's the idea for exact derivatives. Now, what should be the dx? Dx, I am going to denote it by h. So the notation, let's recap. In time, in my course, I follow delta t as my time step, but in real space, delta x is often denoted by h, and I follow this in my book as well. Okay, so h. So there is a criteria by Nyquist. So if the smallest wavelength is lambda min of the signal, there's a signal, there's a smallest wavelength is, let's say, lambda min, then your h or dx must be lambda min by 2. Now, I will not prove it, but you can easily show it yourself that if I have 2 points, well, if I have wave like that, a smaller wavelength, then I need to pick 2 points. Here is the maximum value and minimum value. And with just 2 points, you can do a Fourier transform and you will get this amplitude A. Okay, so I request you to do it, and you can check that if I have, this is my lambda by 2, right? This is lambda by 2. And I just need these 2 points. So my whole wave is that, and it's easy to show that my dx must be this is a dx, okay, which is lambda by 2. Okay, anyway, so this criteria is a very important criteria. What should be the dx or h? Now, given that, you can easily show that k max times maximum wave number, which corresponds to lambda min, times h, which is the dx, which is pi. Okay, so you just straightforward 2 by lambda min times lambda min by 2 equal to pi. Okay, now let's say I want to do this derivative using finite difference scheme. So I will take a simple function and I want to get some analytical results. So my function is e to power ikx. Okay, and my dx is h. Okay, so my derivative using central difference scheme, this central difference. So what do I do? Central difference is f xi plus h minus fx minus h by 2h. Substitute this function, then I'll get I sine kh by h times fxj. Okay, so this is a state formula. I mean, you just substitute, you'll get this. Okay, now we can rewrite this as I sine kh by h fxj. Now, what is the exact derivative of this function? Exact derivative is I k fxj. Okay. Difference between finite difference and exact is obvious, right? And this is there's a difference. We can get to k when h goes to small. Okay, so this is only possible where it tends to. So this coefficient will go to tends towards k for small h. Okay, and this fact is called k tilde. Okay, so I got it here. K tilde times h is sine kh. Okay, so now if I use higher order schemes like where I use 3 points, 4 points, okay, then I get more complex formula, and I is sitting here. Okay. Now we can plot them with. By the way, so the derivative will exact spectral. No? We do Fourier transform. I'll get for that particular k amplitude, and I just do inverse transform, and I'll get exact value. So Fourier is k tilde is same as k. So this straight line is Fourier. FD2 is sine kh, no? So sine kh is this black curve. And FD4 is slightly more complex function, it is here. Now, so you see that this is exact. Now, I am close to exact, not really exact, but I am close to exact till here. But till kh equal to half, finite difference and Fourier will approximately the same. Okay, so that is why we say that basically kh, the FD is a Fourier finite difference. Kmax times HFD is less than equal to half. Okay, why did I put Kmax? The error is maximum when K is Kmax. Okay, so I want to ascertain there are more Wave numbers, so we have to satisfy this relation for Kmax less than equal to half. Okay, if this is satisfied, then of course for Kmax by 2, it will anyway less than half, right? So k equal to 1, of course, it will be less than half. Okay, so what's the ratio between the two resolutions or 2 dx? So HFD by H spectral is 1 by 2 by pi, it is 1/6. So it tells a very important result. It says that the resolution for finite difference scheme, the dx, must be 1/6 or basically 1 by 2 pi, which is approximately 1/6 compared to spectral. So spectral is very accurate. So you need only, if I need 100 points in spectral, I need 600 points in finite difference. Okay, so I'm rushing right now. I'm short of time, but I hope you get the idea. Now, this to illustrate by the same function. So these are discrete points. Huh? So I've taken, I think, 16 points. Okay. So with Fourier is exact. So you get exactly for sine x. I think it's sine derivative sine 2x. So derivative is minus cos 2x. Cos 2x, and this is a function. So my derivative is exact using Fourier. This Fourier is red. With finite difference, there are errors. You can see that this is exactly not sitting on top, and here they're not sitting on top, and there are larger errors at the endpoints. Okay, this is because I'm using Python functions, gradient. Gradients are not good at the ends, not accurate at the ends. Okay, So this illustrates that Fourier is very good for computing derivatives.